Hello everyone. In this video we're going to be going over Lab 8b, the Week 9 lab, where we have to compute the recursive Fibonacci function. So let's see how we go about this. Up here I have my definition. You can see that if we have 0 or 1 we just return the value. Otherwise, if we have n, we return fib of n minus 1 plus fib of n minus 2. And that's us happy. So we're saying that a0 is an n. And we're also told that we want to call the counter subroutine to count the number of times this code is executed. So let's do that. Well, first I've given it a label, and what I'm going to do is I'm going to add immediate to the stack pointer a value of, can't type, of -8 to create space for two things on this stack. There's a stack frame. Now I'm going to store onto that, as usual, the array, and I'm going to store onto it the value of a0 because I'm going to need that, and also if I call the counter subroutine it may well overwrite the value of a0. So we save these values down. And then I'm just going to jump and link to counter. And this is our call to counter subroutine. Okay, once that's done, what I'm going to do is I'm going to load back into a0 the value of a0 from stack pointer, because I want to make sure that that's not been modified by counter. So now I have the value unmolested back. So now I can focus on doing the actual coding. So what I'm going to say is branch greater than a0 is greater than 1. I want to go to the large section, or less than 1 actually, so if it's not 1 or 0. And then if I am in the case where it's 1 or 0, I want to move that value into v0. So I'm going to say move v0, the value in a0, because this is following the base cases up here of 0 and 1. So I just want to move that value into the return register. And now I can start doing the large code. So for the first recursive call, what I want to do is feed it n minus 1. So it's a value in a0 minus 1. So I'm going to add immediately to a0, value of a0 minus 1. Like that. So that gets me my n minus 1, and then I can jump and link to fib. So this is going to be fib of n minus 1. So far so good. Now the problem is I've just updated a0. Fib might overwrite a0 further, so I'm not going to have the value of a0 that I want. So I need to load that word back from the stack pointer. And then what I also want to do is I want to store v0 back to the stack, because that first recursive call to fib is going to produce a value in v0. Now to calculate it I need two calls to v0, so the second one will overwrite what the first one did. So I want to save that value to make sure I can get it back and add it to the total. So what I'm going to do is I'm going to store word of v0, and I'm going to overwrite for VSP. So this is overwriting a0, but I don't need that anymore as long as I carry out the next recursive call properly anyway. I won't need it again. So now let's just do add immediate to a0 minus 2. And then I want to do my jump and link to fib. So this now is fib n minus 2. So we're good so far. Now I'll have the value, or the return value of fib n minus 2 in v0. So now I want to make sure that I can add to that the value from the first recursive call, because up here it's the sum of the two that makes fib of n. So what I'm going to do is I'm going to load word into t0. That's one of the temporary registers, so I'm free to use that as I wish. I'm going to use sp, get result back, and now I'm going to add this to what's in v0. So this is fib of n equals fib n minus 1 plus fib n minus 2. So that's me got my result, and I'm more or less finished. So what I can do now is I want to have an end. Oh, and I've just spotted a mistake. So I want an end label. Well, my mistake was up here I didn't jump to end because I don't want to execute all that code if I'm at the base case. I want to finish. Now that I'm at the end, I can do our usual thing of loading back the return address, destroying the stack pointer or the stack, and then exiting. So I'm going to load word to RA from SP. And then I'm going to add immediately to the stack pointer value of 8 to destroy stack frame. And now that that's done, I can just happily jump back to the return address. So that should be me. Let's assemble this and see what happens. Oh, I've got a capital S instead of small s. Let's assemble that again and see what happens. So there we go. No errors. Fingers crossed it works. And you can see that this final one takes quite a while to execute. So one thing that was really cool about this exercise, at least I thought so anyway, is it counts the number of calls. And you can see the count really explodes massively. So this call for Fibonacci of 19, so it's only the 19th number in the series, is 13,500 recursive calls. So this is a really inefficient way of doing this. And it's because it repeats a lot of calculations. So fib of n minus 2 will, or n minus 1 will reduce to the same cases as fib of n minus 2. They'll just have different ones, but I'll have a couple of different ones, but they'll have the same cases at the bottom. So if we had fib of 5, this would reduce to 4, this would reduce to 3, and then in the next one when we have 4 here, that would also reduce to 3, and then we'd have another one that reduces to 2, and another one that reduces to 2, so you'd have a lot of repeated calculations. But that's not important. So that's how you would tackle this question. Now one thing that was quite important to note was that you need to do this. If I don't do this, let's assemble it and see what happens. So I get an arithmetic overflow error. So that can only be coming from one of these adds. So if I do add unsigned here, I assemble it and I try again, then you can see I get 0 out of 5. So clearly this counter really must mess with the value in A0. So you want to make sure that you have that there, and then you'll get, whenever it finishes executing, you'll have your full marks. So I hope this was useful for you. If you have any questions about Lab 8B, please do get in touch. Thanks.